Hello and welcome. I'm Terry Siggins. I'm the Global Marketing and EMEA Sales Director for Brüel Kjær Vibro. And today I have with me Carsten Andersson, one of the driving forces behind Brüel Kjær Vibro over the past 40 years. Hello, Carsten.
Hello, Terry. I'm looking forward to our conversation.
Tell us how you started at Brüel Kjær Vibro and over your many years with the company, how your career has taken shape.
Yeah, I started many years ago in 1979 at what was called Brüel Kjær at that time. I've always been a part of our condition monitoring team. The roles I've had has included software developer, system architect, project manager, and product owner during my time. Today, my title is development and application advisor. And I'm gradually winding down into retirement. Due to my age, I'm now also spending time on other activities with my family, enjoying my grandchildren, house and garden. I try to keep myself fit by physical exercise, and I'm especially fond of cycling.
Moving on to your time with us, Carsten, what are some of the major developments that you've been an integral part of?
Yeah, shortly after I started at Brüel Kjær, I came into a small team where we developed the battery-operated vibration analyzer and together with a related software solution, machine monitoring software type 7616. This was a great project and I learned a lot, which I still use today actually. We were a small team, which was appointed by Mr. Kjær, and I'm still grateful for him that he actually allowed us to play in a sort of a sandbox.
Yeah, must have been fun.
Yeah, it was fun. We were young guys, all of us, and we just had an old guy in front of us to pave our way through the company. Next, I was after that project, I was put on the development team, which developed the predecessor of Compass, and it was actually a customized development for Statoil for the Colfax production platforms. It was a one-off project and installed on, I think there was 4 or 5 platforms. But all the experience from that project was put into the Compass system, which we had been sold for many years. I was on the data logger project and related Compass offline monitoring software. In the early 90s, I got the project at the advisor machine diagnosis software. After that, I was involved in the first version of the Windows-based monitoring workstation for Compass in the early 2000s. And eventually in 2003, I became a member of a small group together with Peter Allpass, Sasha Good, which are still, and Peter and Sasha are still in the company, and Richard Becelli, who started the wind turbine monitoring business, also known as a remote monitoring group. And this has resulted in the development of a series of products we know today as Vibro Suite, DDAW2, DDAW3, and its, you would say, brother VCM3. Same product, different names.
So I've been in the company for 3 years rather than the more than 40 years you have, and I know that VCM3 stands for Vibro Condition Monitoring 3. Yeah. So what does DDAW stand for?
The Diagnostic Data Acquisition Unit.
Okay. Yeah. Thank you for sharing that.
Yeah, but I think we are talking a little about that later also. So today my current work is to advise in developing the SaaS solution and the continued development of DDAW3, VCM3, and also Diagnostic Analyzer and Vibro Suite.
Okay, and you've done a little bit of work on standards as part of the committee. Could you share that with us?
Yeah, this is actually something I have been very happy to work with. It is one of my big interests as I see standards as very, very useful in our business. Unfortunately, they're not. I don't think they're used enough. but the standard that I was developing was under the ISO TC 108 SC5 in the work group 16, where I was chairman of the, you could say, wind turbine condition monitoring development. So we developed two standards, the ISO 16079-1 and ISO 6079-2. I was also taking part in standardization work on the IEC, where I have also been contributing author of IEC 61400-25-2 and 6, which are, you could say, standards describing the data model for you could say data from wind turbines.
Okay. So look, so you've been involved. There's a lot of achievements there from the early days of wind turbine monitoring. So could you expand a little more on the leadership role that you took within developing these things, and what were the challenges that you faced to get this technology up and running?
Yeah, in the beginning, as it all started, this wind turbine monitoring market was driven by German insurance companies who offered a lower insurance cost if the turbines had a condition monitoring system which were fulfilling the requirements of Anomalies, which now is called DNV. Right. At that time in 2003, BKV was contacted by the wind turbine manufacturer NEG Micron, who asked whether we could offer a solution for the turbines as they needed a product they could offer to their customers as a response to the requirements from the insurance companies. So this was the start of a remote monitoring group in Denmark, in beginning only with 4 people, which were led by Peter Olpas.
So what happened? What happened next after this?
We proposed a solution to NEG Micron based on the products we already had on the shelf, so to speak. That is the compass system as a software solution and the database for measurement data. And then we used the Vibro IC, which had been developed in Darmstadt, as the front end. The Vibro IC was located in the wind turbine and was mounted together with 2 other hardware products, which was developed by a company called IoTech, which now is Preves. So we have had that partnership for a long time.
Wow.
And it was consisting of the DDAR1 for acquisition of time waveforms, and a little web server which transferred all the data via the mobile network to our servers located in our server rooms.
Right.
While this was done, the development of in Preves, we developed a software solution to analyze the data, where we interfaced the Compass database to the data acquisition servers. A new web-based wind turbine data management system was made, and we made tools for analysis of wind turbine data, which is known as the VTD analyzer and reporting tools for alarm reports. Then the story was that in the middle of all that, NEG Micron was acquired by Vestas in early 2004. We knew that Vestas was working on their own condition monitoring solution for wind turbines. So we worked day and night to finish our solution and get it certified before the date when NEG Micron officially merged with Vestas.
Right.
We thought our position would be better if NEG Micron had an operational solution which was certified by Anomalies the day Vestas took over NEG Micron, because Vestas was not that far in the development.
So I think because we're here talking today, you made it in time.
Yeah, we did. Yeah, it was hard work, but very exciting, I think. I'm very grateful also for that part of my time at BKV, because we had a small team. We took all the decisions ourselves, and we had close customer contact, which I enjoy.
So how did you celebrate your successes then?
Yeah, what we did, I still remember we started getting turbines online, but it was a slow process. Vestas management was not so convinced that condition monitoring was something that worked. Strange thing was that some of management were even worried that if they offered a condition monitoring system, it would be the same as saying that the turbines could fail. Everybody knew they failed, but saying it officially actually was a problem for them. But we managed to grow the business, and we celebrated it. First, I think it was 200 turbines online, then 500 turbines, then 1,000. And then we stopped celebrations because suddenly the Vestas business started growing, which I call the ketchup bottle effect. We have been awaiting that for many years, and suddenly it started actually growing exponentially.
Why the ketchup bottle? I'm interested.
Yeah, it's like, if ketchup is stuck in the bottle and you shake it, and suddenly
right.
Yeah. That's why we call it the ketchup bottle effect.
Okay, thank you.
Of course, in parallel with that, we also started selling our systems to other customers, like wind turbine operators, and that also brought more business to our remote monitoring group. So at that time, from the 4 persons in 2003, I think we were between 25 and 30 people working in the remote monitoring group, either with development or with monitoring the turbines.
It's fun times in a cool business.
Yeah. It was great. So yeah.
So how did that growth continue in service and in products?
Yeah, we grew until around 1,200 turbines. Then, unfortunately, Vestas made it a part of their strategy to do condition monitoring in-house, and as they wanted to start to offer their own service products. We were in tough competition with other wind turbine monitoring vendors, but Vestas ended by basing most of their CMS business on our products, including VibroSuite as their condition monitoring software. It was a strange process, as at the same time there was a kind of competitor, but we have to give them all the help to get success, otherwise they would not buy our products.
Right, it's an interesting dynamic.
Yeah, very interesting. But I think we have all the time, we had quite a good relationship to Vestas, and this is the same today, where we have good contacts with you could say, the people doing all the CMS work.
And how many systems do we have today in the field?
I think we have reached nearly 40,000 systems.
Wow.
And that's a lot. If somebody had told us that when we started, we would never have believed them. I have never been in a project that has sold that many systems.
I believe from some history that once somebody told Per Brüel, who founded our company, that it was an interesting business, but there would never be enough revenue to support 2 people. That was
yeah.
So how has the business and customer expectations evolved from the early days of those first wind turbines?
Yeah. Yes, as maybe mentioned before, we had to make continuous improvements to keep pace with the growing demand for increased turbine monitoring efficiency. We had the problem that the stock of our Vibro ICs ran out, so we had to develop the new hardware for DAW2. It happened very fast. Only within 10 months, we had the first park online, and then it had to be approved. And we started developing also VibroSuite, or you could say the predecessors of VibroSuite.
Right.
We had to do all that while the system was running, so it was a bit tricky sometimes to introduce new products. while we were not allowed to lose any data or stop our systems because we had to do monitoring all the time. In the beginning, our services were to deliver half-year status reports, which gave the customers an insight into what would happen in the next half year.
Yeah.
In parallel with that, we also delivered the alarm report service, where we submitted an alarm report, maybe to a service company, as soon as a fault on a turbine was detected. The need for status reports in the form that we made it died out. So now the focus is on the alarm report business. This has also changed a bit, you could say, in my opinion, because now we have, when we submit an alarm report, we have 4 severity levels. Severity 4 is the first indication of a fault and gives a very early indication, maybe 1 year before a fault happened. We can actually,
well, that far ahead.
We can detect a bearing fault, but of course there's a long time to break down or to failure.
And how do you go from 4? I presume if 4 is simple, you go 4, 3, 2, 1. What do the different levels mean?
That's our, you could say the difference is the lead time. So if you have a severity 3, I'm not really aware of the current lead time, but I think it's around a couple of months you get. And for 2, it's 14 days. And then we start watching the turbine and telling the customer, now you have to prepare your service team. It's getting closer to breakdown. Severity 1 is where we advise to stop the turbine. Our concept from the beginning was always to provide an alarm report only when we were certain that a fault was present. There's no reason to send an alarm report telling that something is wrong, but we don't know what it is. So everything had to be confirmed by a diagnostic engineer, and our goal was to provide these highly reliable reports. So when we reported a fault, there was a fault. And we tried to push the lead time as much as possible.
So how has it changed? How has it changed between your original concept and today?
Yeah, as the recent development is that picture has changed for the wind turbine operators and you could say companies like Vestas. They have to run the turbines closer to breakdown and maybe even possibly derate them to reduce the load. And the reason is actually partly because of the lack of service staff, because you have more and more turbines erected.
Right.
And partly also due to a lack of spare parts. If you order 100 bearings, maybe you get 10. So you have to run your components much further than you used to. This actually led to our most recent development in the remote monitoring group, where we moved the stop or go decision into the monitoring device in the turbine. So now there's no diagnostic engineer in between. Our diagnostic unit has been extended with intelligence that enables it to send an automatic stop or go decision to the turbine controller. So there's no alarm report anymore. Of course, it's also sent to our servers where it's reviewed, but if they need a fast response within minutes or hours, they rely on a stop and go decision. And this is a very important step for the condition monitoring system, because now it's moved into the control room with a daily operation and has another focus than if you send an alarm report to a maintenance department who plan maintenance 3 or 4 months in advance. So it's really, you could say we are in the hot seat there. But I think it's very interesting. And I think that also indicates the direction when we move forward, that devices shall be intelligent, information from the devices shall be easy to interpret, especially for the wind turbine, but I also see that as an application for other types of machines.
So would you say we've moved on from people not wanting condition monitoring to this being seen as an essential part of running a wind farm.
Yeah, it is very essential, and we hear from Vestas that really people are calling the department for, you could say, condition monitoring and asking them questions. How does it look? Can you do this and that measurement? We have a problem. We need some root cause analysis. Can you give us some data? So it's not only monitoring data we have to deliver, but it's also data you can use for root cause analysis. And this is where DDAO3 is a very good tool, because we can provide very long time waveforms for analysis, and it's totally different from you could say from the monitoring part, but
Right.
Still the device has to deliver both, because they see actually failure modes in the large turbines, which they cannot really explain. They have actually scaled up the smallest, you could say, 50 kilowatt turbines into a 5 megawatt turbine. Same technology.
Does that work? Does a big turbine behave the same as a small turbine?
It's working in the same way: a generator, a gearbox, and a main bearing. And they have just scaled it up all the time.
Yeah.
And maybe with the very big turbines with towers of hundreds of meters, they have another dynamic. There are some effects on them that they need to investigate. And this is, I think, where we can contribute. One of our wishes is also to make the trigger facilities of DDAO3 even better, so we can react within seconds and provide the data.
So are we able to capture new faults that we haven't seen before?
We're able to at least to catch data as a reaction on events that happens in the turbine. All the, you would say, this kind of analysis is done by Vestas. It's not done by us. Our business is still based on you would say the monitoring, but Vestas uses it for research and for their root cause analysis. And this is not something we have been very much involved in. They ask us to provide the data and set the requirement for our device, but they do the analysis. Of course, they sometimes lift the curtain a bit, so we can know a little of what they're doing. But this is something they're very concerned about.
Well, most companies these days are find value in the data that they have.
Of course, all the recordings of time waveforms, eventually they can turn into, you could say, descriptors you can monitor, thus improving the condition monitoring system.
So with all the turbines that we've monitored over the years, so we must have collected a huge lake of turbine monitoring data. So can you share with us what we're doing at the moment to improve our techniques for analysis, the analytics, including anything in artificial intelligence or machine learning?
Yeah, we have a lot of data, and throughout the past 2-3 years, they have been investigated using, you could say, AI methods or machine learning methods on those data. I think the concept of AI is a bit difficult because you could say it's a sort of buzzword used everywhere. But in my understanding, AI is when you replace human reasoning with algorithms executed by a computer, and it's not specific algorithms. Because what I've been working with in the past, and what's most relevant for us in the future, is what you call a narrow AI, as opposed to general artificial intelligence.
What's the difference?
In narrow AI, we use a collection of technologies that rely on algorithms which can be deterministic and statistical, to simulate intelligence. That is, we have focus on a specific task, like finding a specific fault on a machine. We know the pattern of descriptors indicating a certain fault. So what we try to do is to recognize that pattern in the data we have. And this is, you could say, described in literature. It's knowledge from many, many years actually collected. So we have experts that can tell us how to do it, and we can study literature to find methods to detect the faults. So there's not so much, you could say, magic in it. It's very important when you see or when you detect a fault by your system, that you can explain to the customer why have the system, why are the system telling me that I have a fault. So you need to document it, because should the conclusion be wrong, you also need to document why it was wrong, because then you can tell it to the customer. If you cannot do that, he would stop immediately trusting other, you could say, diagnostic results from the system. But it's very important that it's out in the open. How did we detect that fault? And this was some of it I worked with in my advisor product, which we maybe talk about later. There's other methods like machine learning, which I consider it's a specific type of narrow AI where we actually have a lot of stored data, and it can then classify them, but it's nowhere near what we call general AI. It's more simulation of human intelligence. And we can dig into a lot of data, and it might not be obvious to an observer, but there we have some advantages of our computer. So I think what we should focus on was actually to utilize AI in the form of narrow AI. We know the data we're looking at, we know where it's coming from, and then we can easily implement fault recognition on the machines. It's not rocket science. The methods are there. We just need to use them.
Okay.
So our data scientists, they actually use the wind turbine data for different purposes. We tried to go in different directions. One was to classify our alarms so we could filter out irrelevant alarms. We get a lot of severity 4 alarms which are not really, will not end up in an alarm. But we also get some severity 4 alarms which will end up in an alarm. And would you be able to classify them and sort them apart? But the results were not 100% effective, so we put it on hold. It's difficult from early data to look into the future. We were not successful in that. Then we have worked with methods to detect anomalies in time waveforms, which is important to detect because the time waveform tells whether the sensor is good, whether the cable is good, do you have electrical glitches and things like that. And we need to take those time waveforms away, so we are not analyzing on garbage data. In some cases, we managed to make methods to repair the data, so they actually could be used for some part of the analysis.
Right.
So it was actually good results, and there was also good results in recognizing fault frequencies on turbines, especially from bearing data with analysis of planetary stages. That was actually quite good. But the problem is when you examine, you would say, slow rotating machines, you need high resolution data. You need time waveforms of a longer duration.
Okay.
And only in the recent years we have time waveforms of long enough duration so we can go back and review old faults. Many of our older time waveforms did not have sufficient duration to produce a reliable diagnosis. But I think they got some good results, but they have not been implemented in any systems yet. Now it is intention to implement these methods in the SaaS solution also. So I think we can use it there.
Okay,
Yeah.
look, we talked a lot about big data, and I realise you can't talk about everything because some things may be confidential. But you mentioned earlier Advisor, which I believe was an early attempt to use artificial intelligence, machine learning. Can you tell us a little bit more about that initiative?
Yeah, I can tell you a little about it. As I said, it was a product I'm very fond of. I worked with it for many years. It actually enabled me to travel around the world, so to speak.
Oh, nice. So I need to invent one of those.
Yeah, we were very involved in support work and presenting it to customers and all that. So it was a very nice time, but it was also hard work getting it finished in 1995. It was continuously improved, and the last version was submitted in 2010, where I extended it to analyze 5,000 line spectra, which was a feature of Compass 6000. Advisor used automatic pattern recognition, again, compared a set of descriptors with a set of descriptors indicating a failure mode, and then you could see how good the match were. It worked very well and reliable, actually. And in that product, I also worked a lot with justification of the diagnostic result, so the customer could see why it had reached a certain conclusion. I don't think that you would say the AI-based automatic diagnosis software will ever be as advanced as you could say the processes running in our brain. But I think a system like Advisor is fully justified by the speed of operations, because we can analyze thousands of data sets in the time where a diagnostic engineer can analyze 2 data sets.
Right.
And we can actually sort them and condense the information, so the operator only have to look at a small fraction of the data sets that we acquire. So
that's a time saving, and also improves the efficiency of the number of turbines.
Exactly. And you could say it's also a training tool for people not knowing much of condition monitoring, because as we document how we reach the conclusions, everybody can learn from it. So in that way, it also served a good purpose.
So it sounds like Advisor was way ahead of its time and an impressive achievement. So
yeah.
It brings me to my final question. So if you look at the leaps in technology, how do you think condition monitoring and diagnostics will change in the future in terms of the requirements, the technology, and the services?
I think it actually will take 2 directions. One will be the device-based intelligence, like I talked about for the wind turbines.
Yeah.
But I think that can also be used for other machinery. When you have device intelligence, you can actually make an on-premise solution which can provide actionable information directly to the control room and then via standard interfaces. So we are not supplying you could say the condition monitoring system, but we provide
we feed it with insights.
Exactly. So like in the wind turbine business, I think that can be extended also to other types of machines, because of the fact that monitoring experts are more and more sparse. They're not on all plants. They have to rely on, you could say, on the machines or on the technology we have in our devices. Another one is, I think, is also where we have a cloud-based service. This can be used where requirements to response time is less critical. And you could say the advantage of a cloud-based approach is that it can take data from much simpler devices or device setups. You just need a time waveform, and then all the analysis is done in the cloud.
Yeah.
And when you have it in the cloud, it's very easy the process of, you could say, updating your diagnosis system is much easier as you only have to change it one place, not to deploy a new,
version to everyone in the fleet.
To everything in the fleet. This is a much more lengthy process, and we can also test new algorithms in that way. So in that sense, we are more in control and can then start, you could say, moving methods that we develop in the cloud onto the device, so it can be used for on-premise systems. So I think it takes two directions. We have to focus very much on our hardware, and I also think for the Vestas business, I think they'll go for the intelligent solution, delivering simple data, but to the Vestas cloud system in the end.
Brilliant.
So, but I think we should not leave or give away the possibility of selling a lot of hardware boxes and also a system that can maintain a whole fleet of our DAW3 units. This is something that we have to do and sell to Vestas. So there's still a lot to do in the wind turbine business, but I think we should think of more and more intelligence in a device. Think of easy maintenance of a whole fleet of DAW3s. Today it's a bit heavy to update a fleet of wind turbines because the operating system and things like that takes many megabytes, takes time to load on a network that hasn't a good bandwidth and all that. So we need to do work there in this area.
Look, so Carsten, in the time we had, I think that's about all we have time for today. And I'd like to say thank you very much for sharing your expertise, your experience, your war stories. Yeah? And may I say on behalf of both Brüel Kjær Vibro and I'm sure the customers that you've had an impact on, we appreciate your invaluable contribution over the past 42 years. Yeah. So from my personal perspective, I'd like to wish you a happy, healthy retirement as you wind down to spend time with your grandchildren.
Yeah.
When that day finally comes, we'll miss you, but you deserve it. So
thank you.
Thank you very much for today.
Thanks. It was a pleasure being here.
Thank you.
Thank you.
Goodbye.
Bye.